Okay, class. Yesterday we did something which is, we did two things, a couple of things actually. F equals to gmm upon r square, g equals to f upon m, which is gm upon r square. Let's see how much of it you remember. Yeah? R over here is the distance between surface of a planet to the surface of the planet, correct? From the center of gravity of a planet to the center of gravity of a planet. So it's center of mass, correct? Center of mass to center of mass. Actually, it's center of mass because I think the notes they treat it as center of gravity as to center of gravity. Center of gravity is same as center of mass. So gm upon r squared. This g over here is known as the gravitational field strength, and it is defined as force per unit mass. And what's the phrase that students will miss out? Point mass, exactly. Remember the point mass because IB looks out for it actively. And these quantities, they are what quantities? Vector or scalar? Vector, yes. And last lesson we did something on this and this over here. And then we found the point where the gravitational field strength is 0. Now today I'm going to up the level a little bit further. I'm going to bring the idea of vector sum of the two masses a little bit further by giving you a two-dimensional case. So say for example, if you have a point over here and a point over here, but under the influence of two masses. This is, let's call it A, let's call this B. B has a mass of 2m, 3l away, and this is 2l away. And the gravitational field resultant points in this direction, and this is, this is 30 degrees. And this is G resultant. So therefore, what I want you to do is to find the mass of A upon B, or rather mass of A in terms of m. What's the number over there? You might find it useful to use or to draw a vector diagram to show how G of A plus G of B gives you G of R. It might help you. And the hint for you is that you need to use a trigo function. And trigo function means sine, cosine, tangent. No worries, you don't have to use secant, cosecant, or cotangent. Nothing of that sort is coming in yet. Yet, yes, correct. So give it a try. I'm going to give you 2-3 minutes to struggle a bit, and I'm going to give you hints as we go along. MA over M, that means MA in terms of M. So if MA equals to MA upon M equals to 4, that means MA is 4M. Yeah, so in terms of M. Give it a try. Remember, this is vector sum, so wiggly, wiggly, wiggly. 8 upon 9 root 3. Is it correct? 8 upon 9 root 3. At this point of time, I think I'll review at least the vector diagram so you can check whether your vector diagram is correct. So remember, gravitational field always pull. So this is GB, this is GA. So if you add up the two to give you GR, the vector diagram should look like this. This is GB plus GA giving you GR, and this is 30 degrees. Therefore, GA over GB will be equals to tangent 30. Yeah, so GA over GB equals to tangent 30, and I know that in the age where we rely so much on scientific calculator that we don't remember what's the value of tangent 30. Anyone remember? Insert form, 1 over root 3. Excellent, excellent. Sometimes I'm very upset when people can't even remember what is sine 30. Come on, 30, 60, 90 you must know kind. 0, 30, 60, 90, 45 as well. So therefore, this will be GMA upon RA squared times RB squared upon GMB. At this point of time, I'll let you finish it off. I'll let you to have the finishing touch. So finish it off, and if you do it correctly, you should find that MA over M is equal to 8 upon 9 root 3. There's a part 2 to this question. Herman, you okay? Now, for those of you who have finished this question and gotten this, for those of you who are still on this, carry on. I think you're doing fine. So for those of you who have finished finishing the question and got this answer, I'd like you to think of this. How far do you need to place a mass of 4m away from this point so that the total field due to the three masses A, B, and C is 0? Let me repeat the question again. How far and where do you have to place a mass C of mass 4m? C has a mass of 4m. How far do you need to place it away from point X so that the resultant field of everything is 0? At this point in time, I'd like to check if anyone hasn't gotten the answer for this yet. Everyone can? Okay, no, take your time, take your time. No worries, take your time. Sorry? Yeah, over here, yes, correct. The point mass is still here. But I'm adding a third mass of mass 4m so that the sum of A, B, and C gives you 0 field at that point. And roughly where is that mass? Evans, you okay? What was the second question? The second question is, okay, after this one, this is the first question. Second question is, if I have a mass C of mass 4m, yeah? How far do I place it from X, and roughly where should I place it so that A, B, and C add up together to give you 0 field at this point? Yeah. That one? Can. Let me show you. Can? Let me show you. No worries. This one GG cancels off because it's a constant. MA upon 2M because MB is 2M. Agree? And then multiplied by RB is 9L square because it's 3L whole thing square. And then this is 4L square equals to 1 upon root 3. Then the next part will be a big cancellation game, and you should be able to find that MA upon M is equals to 8 upon 9 root 3. Can? Yeah. Hannah, can you see this? You can, huh? Okay, good. Excellent. Then you proceed on to the next question where I have a mass of 4m, messy. It makes the question a bit messy. So the thing is, where should I place it and how far from X do I place it so that it becomes 0 field at this point with A, B, and C added up together? So where should the mass be? First question. Is it going to be down there? Correct. It has to be somewhere here. In exam question, if I give you a physical diagram, I want to see you drawing a dotted line backwards. Dotted line backwards and somewhere here. So it's not just anyhow gasak kind. It is You show understanding that it is directly opposite. Well, the concept is that if the resultant field is 0, then the field at point x due to c must be equal and opposite. The magnitude must be equal, but direction should be opposite to GA plus GP, which is GR. Okay? It has to be equal and opposite, so that it cancels away. First statement, any disagreement? Okay? Now, then from here, there are two ways of doing this, the hardworking way and the smart way. Yeah, the hardworking way will be, see whether you're the hard worker or diligent worker or the smart, street smart person. If you had taken square root of GA square plus GB square, you're the hardworking type. Nothing wrong, it is good, it is good. It is nothing wrong, it is good. If you do it correctly, you get the answer. But the smart type will be, you see GB, GA, and GR. Isn't GR equals to GB divided by cosine 30? Agree? So you only need to handle one G instead of GB, GA. Higher chance of mistake, agree? GB squared plus GA squared square root. For this method, you only need to handle one G. So why did I choose GB? Why not GA? Make a guess. Exactly, the mass is nicer, right? Rather than handling 8 upon 9 root 3m. Yep, that's why. It's a conscious decision to choose B as compared to A. Can? And then you just need to work out the distance and ta-da, nicely. You got the square root of square root, is correct. So don't worry. So this is about the most difficult question you can find in IB, I think. It is still in syllabus. But the concept, don't lose sight of the concept. The concept tested is only on the vector sum of field. That's the only concept tested. Just that it gets more and more mathematically challenging. Ken, do you agree that if you were to take a trigo function, that this is the hypotenuse, this is 30 degrees, hypotenuse and adjacent? So GB over GR is equal to cosine 30. No worries, no worries. It's just sometimes yeah. Okay. Now I'm going to show you very soon how you can actually derive, and probably how Newton derived the idea that the gravitational field is Gm upon R square, that the inverse square law. It's a very important law that is derived from very fundamental concepts and a little bit of differential. A little bit, not a lot. It's a, yeah, not life-threatening kind of differential. Very, very friendly. I'll go through the concept first, and then yeah, I'll go through the math. We need to get the picture right before we go through the math. Can everyone? Okay? Comfortable? Yeah. Remember, don't lose sight of, whenever you see a question, what concept is it testing? This is testing on Gm over R square and vector sum. So don't lose sight of the concept. Now remember last time I mentioned that if you were to throw a rock, whatever, I mean, why you want to throw a rock off the mountain, I don't know, but if you throw a rock, it will come down like this. If you're strong enough, it will clear the foot of the mountain. Yeah? Now if you throw it harder, it will go like this. And then remember I mentioned that if you throw hard enough, it will hit you from the back. After about 45 minutes later, actually 1.5 hours later. Yes, it's about 1.5 hours orbital period for anything that's close to Earth. It's about 1 hour for 30 minutes. Now, can you therefore see that this is a what motion? Circular, right? So this is a circular motion. But this is also a, can you see this, and this, they are also not SHM, projectile, exactly. So let's take a look at what sort of magic we can play from here. Yeah, let's see what, so this is the idea, that an orbital motion, which is a circular motion, is also a projectile motion. Can? Now let's see. So if I were to throw something at a speed v, after some time, it's going to have the same horizontal speed, but it's going to be at an angle. You okay with that? So it will have gone through an angle. Let's call it. Now you should be able to smell differential coming in soon. A small little angle shift after a small little time. The object will have gotten this way. Still okay? Can I? Now do you agree that this is the dv, which is actually equals to g dt? The vertical velocity gain is g times dt. Still okay? Still okay, huh? Still okay, huh? Okay, good. Now, do you agree that tangent d theta is approximately d theta? I don't know whether you have learned this in math, but in radians mode, tangent theta is approximately theta if theta is small. If you don't believe, switch your calculator to radians mode, tangent 0.001, you get 0.001. Okay, so this is actually an approximation. The full glory of this approximation is tangent theta is approximately theta minus, I think, theta cubed over 3 factorial, if I'm not wrong. That's the full glory of things. No, this is just to explain to you the math approximation. But because if theta is small, this goes to 0. That's why this is true. Okay, can? So therefore, tangent theta is equals to g dt over v. Now therefore, d theta dt, which is equals to g upon v. Now this, remember, it is actually your omega, the angular speed, which is v upon r. Therefore, v squared equals to rg. This is an important step. Still okay? Still alive, huh? Still alive, huh? So if the object is projected such that it can go in a circular motion, in fact, this one we're using circular concepts already, because d theta dt equals to omega equals to v upon r is actually circular motion. On the right side of this equation, it is projectile still. So we are merging the two together already. Can? Now, so v squared equals to rg. Still okay? Now, do you remember that v is equals to 2 pi r divided by t? So if I v squared this is going to be 4 pi squared r squared divided by t squared. Still okay? Therefore, if we equate this to rg, you have t squared equals to 4 pi squared. There may be a mistake somewhere. V squared equals to rg equals to v equals to 2 pi r divided by t. And if I square that, 4 pi squared r squared divided by t squared. And therefore, t squared is equals to gm 4 pi squared r squared. So therefore, this will be r upon g. Still okay? Now this is where Newton depended on someone else. The name of the person starts with a K. Kepler, correct. Kepler. So Newton stopped at this point. But Kepler said something. Kepler said that t squared from data observation, that t squared is proportional to r cubed. From observation of the stars, movement of the stars. And therefore, can you see that if you combine these two together, you can deduce that G must be proportional to 1 upon R squared. For this to be R cubed, this G over here must be proportional to 1 upon R squared. Yeah? Therefore, Newton came up with this idea that gravitational field is an inverse square field. So he postulated that G must be proportional to the mass of Earth or the mass of the stellar object divided by R squared. And you write an equal sign by putting this constant over there. I'll give you a little bit of history. In Cambridge University, there is this experiment called the Weighing the Earth experiment. It's done by someone called Cavendish. Yeah, it's still called, the laboratory is still around. The laboratory where he worked on, it's called the Cavendish laboratory for obvious reasons. Can you see that if you know the radius of the Earth, which at that point of time where Cavendish lived in, they know the radius of the Earth, and you know the acceleration of free fall, if you can actually calculate this constant G, you will be able to measure the mass or calculate the mass of the Earth. Make sense? Now, how did he do it? What he did was, he put two masses over here, and then he put two other masses over here. And do you agree that there will be force of attraction between these two objects? So what will happen to the string? The string will start getting twisted because of the moment. Agree? So the string will get twisted, and the string will not twist forever. The string will exert a returning twist. So the moment exerted by the string was equals to k theta, and moment is equals to force times distance over here. So all he needs to is to measure the angle. This can be found using another experiment to measure how much twisting moment that the string gives per angle. And knowing the distance between the string and this one over here, I'll be able to calculate the force. Now remember, F equals to GMM upon R squared. If I know the masses of those two masses over here and these two masses over here, I can calculate the force over here, and I can measure this distance over here. I will be able to find the value of big G. And that was exactly what he did. And after finding the value of big G, he plugged it inside here, knowing that this is 9.81, knowing the radius of the Earth, he calculated the mass of the Earth to be about 6 times 10 to the power 24. And you must know how powerful that is. For a man who is only about 60 kg to measure the mass of something which is 6 times 10 to the power 24. I think that's really amazing. And that was done in a laboratory setting. It's really, really amazing if you think about this. So everyone stood on the shoulders of everyone else. Newton stood on the shoulders of Kepler. Cavendish stood on the shoulders of Newton. And it just goes on. It's a series of people standing on each other. So one day, you'll be standing on the shoulder of someone, hopefully. And then seeing more, seeing further. Okay? So I'm just giving you a brief history. No worries, IB is not going to test you on this. Write down the history of G. But I thought, as a physics student, as a good physics student, you must know that chain of knowledge building. Yeah? That chain of knowledge building is important. That you are never working, or if you invent a new idea, it's never something that you invented, you're developing from someone. And that's intellectual humility. Cool? Can? So we're slowly moving into the advanced part. Ready or? Ready for the advanced part? Okay. Go and check out more on Cavendish Experiment. It's called Cavendish Experiment. The name is Cavendish. Cavendish. Okay. Okay, let's go. Remember I asked you to think about something yesterday? What did I ask you to think about? Yes, a rod. How do you go about finding the mass of attraction between mass of Earth and the rod over here, which has mass m? I'm going to show you how to do this, which is the easier one. Then I'm going to give you the more difficult one. Okay, let's see. Do you agree that there's a small mass dm? The force of gravitation on this small little mass is going to be G, mass of Earth, dm upon r squared. Where r, okay, probably I use x so that as not to confuse with the r. Where x is the distance between the center of Earth to that mass dm. Okay? Okay. Now, do you agree that this is gm dm? Let's call this thing rho, which is the mass per unit length, times dx upon x squared. Still okay? Make sense? Rho is the mass per unit length. So if you take m divided by 2r, you get rho. It's the mass per unit length. I'm assuming it is a uniform rod. It'll get more interesting if my rod's mass changes with distance. Yes, it is possible if I want to make your life even more interesting. Can. The rho is actually mass per length. So mass per length times the length will give you that small mass dm. Yeah, and the mass per length in this case is m upon 2r. We'll put that back later on. Okay, we'll put that back later on. Is my time up? Or okay. Is it like you? Does it look like your dad's number or okay? In case it's dad's or mom's. Okay. Now df is equals to gm rho dx upon x squared. Now if I integrate this from 0 to f, I integrate, guess what's the limit? What r to what r? What x to what x? Take a guess, what's the limit? From here to here, so it must be? No delta r lah. 0? X is 0? 2r to 4r, exactly. Yeah? Make sense? Because from here to here, from here to here. Hang on. Now the good news is that gm and rho are all constants. They're all constants. So it will be gm rho integral from 2r to 4r 1 upon x squared dx. And come on, can I have faith that you're able to integrate 1 upon x squared? Go ahead and do it. Come on, find the f. Go ahead, try. I give you 2 minutes, at least wiggle your way through. It's a simple integral. The next one is going to be difficult.
What? There's a next one?
The next one, yes. There's a next one. You see, I can make your life even more difficult by having, like what I said just now, a one where density changes with distance. I can stack the rods up to form a plate. Okay, because if the x over here, if I have a rod that is of negligible length, then it should have negligible force. Yeah? So when it's 0 length, at 2r over here, it has 0 length. So it should have 0 force. So when I go from 2r to 4r, sorry? So if I have, say for example, 2r and, okay. That means at this point, it will have 0 mass because there's no dx here. Yeah, then as you lengthen it, that's when the force has to increase to f. Can? So it's gm squared upon 8. Actually, it's not gm squared. Did I put the same m? Probably it's gm and small m. Okay. Cool. Not too difficult, huh? Can do or not? Doable, huh? Doable. Hopefully. For those of you who have done this, I'd like you to think about this. Dun 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 dun. Huh? 怎么办? Right, now the challenge over here is this. Now the force of attraction, this dF, is at an angle. But do you agree with me that the good thing is, if you have an opposite point, do you agree that the vertical forces will cancel out? So it's only the horizontal force that will add on. But because of that, you need to take the component of the force, which is, if this is called theta, is it cosine or sine theta? It's dF cosine, sine or tangent? Cosine theta that adds up. So this is the one that you want to add up. Bling, bling, bling. Can you understand? This is, let's start with the basic idea first. So we're only focusing on the horizontal component. The vertical component will subtract away. Cool on that? Before we move on. Still over here. Still hasn't rotated yet. Okay, which part of this derivation are you a little bit lost or you don't understand? Like one step to another step, one step to another step. The critical is the setting up of the integral law. That's the critical part. The critical part is the setting of the integral. The second part, which is critical, is the limits. Those are the two critical steps. So ask yourself, do you understand why the limits are the way they are? Second part, do you understand why the integral is as the way they are? If you understand, rest assured, the rest is math. And rest assured that you're still within sight, and you haven't gone into outer space yet. Cannot. Guys, the way you're looking down is very worrying. Are you okay now? Yes, Shedding.
What is that?
What is that? This one okay first or not? Okay, yeah, okay, that one's clear. Okay, now this one. This one is the same rod. It's the same rod. All I did is to flip it. Yes, correct. Which is yes. I'm gonna guide you through. Chill. I'm gonna guide you through. So, but let's do it step by step. At every critical point, I'll slow down a bit. The first critical point is, do you agree that the vertical will cancel out because this one and this one symmetrical? What? So it will cancel out. For every point above, I'll find a corresponding point below where the force vertical would be the same. So I only need to consider the x component. That's what I'm trying to say. Can? So therefore, dfx is equals to gm dm upon, let's call this thing over here, let's call this r squared. Okay, so this distance over here is your small r squared. Cool? And then cosine theta. Okay, ma? Still alive? Once again, okay. Let's take a look. R is here. R is here. From the point to the dm that I'm considering. This is my dm. Okay? So that's the R. The distance, remember, the gmm upon r squared is the distance between the 2 points, the 2 masses. The 2 center of mass. The center of mass over here and the center of mass over here. And the cosine theta there is basically to address the horizontal component. Can I? So this is first critical step. Now the second critical step. G, M. Okay, I'm going to set up the coordinate system. This is the y-axis. Y-axis, nothing more, right? I'm not throwing like rocket science here. This is the y-axis. What? Haven't you seen the y-axis before? It's like, relax. So this is the y-axis. So do you agree that this is the same thing? Mass per unit length times dy. Same as what we did just now. Instead, that was x. Now we go y. That's all. Right? I haven't introduced something like some matrix or whatever here. Just rho dy. Same thing as over there, just that was rho dx. Cannot. Still okay, huh? Okay, now here comes the fun. Do you agree that r squared is equals to 4r squared plus y squared? Pythagoras. Relax, before your jaw drops to the ground. Do you agree that if I call this y, this is 2r, this will be 2r squared plus y squared? Pythagoras. Times cosine theta is equals to 2r divided by r. 2r divided by r. Theta, adjacent, hypotenuse. Before it starts confusing, it's like, Okay, no. Adjacent, which is 2r, hypotenuse, which is r.
I look at the rho dy.
Okay, rho dy, I'm just using the trick that we used just now, where dm is equals to rho dx. So the mass, small little mass, is equals to mass per unit length times that small little length, which is in this case in the x direction. Now my distance moved is in the y direction. So it's the same strategy of using mass per unit length divided by times the small distance that I move in the y direction. Okay. Now this will be equals to gm rho dy over 4r squared plus y squared times this one. Why? Why? Because do you agree that this is square root of 2r squared plus y squared? Which is actually this thing over here, just that this has a square root. So this times this will give you 3 to the power 2. And 2r is here. That's all. Still okay? So let's put everything together and tidy things up. 2m rho r dy over 4r squared plus y squared to the power of 3 upon 2. I'm just rearranging things. I'm multiplying this. I'm shifting the 2r, all the constants out. And then the y over here. Okay? This is easy compared to proof by induction. Yeah, which is easy. Proof by induction, easy. Now, what I'd like you to do is, okay, let's clear things up and write dfx is equals to 2gm rho r times dy upon 4r squared plus y squared to the power of 3 upon 2. Now, I'd like to give you an integral, and the integral is this. A squared plus y squared to the power of 3 upon 2 is equals to, and even I myself can't really remember the integral, so I have to copy it down. Y over a squared plus y squared to the power of half. Given this integral, given, relax, given. So using this, can you see if I were to integrate this, do you agree that this will be 0 to fx, which is the resultant force we want to find? This will be from minus r to r. Okay? Minus r because it's below, r because it's above. This is the midpoint. Minus r to r. Would you like to give it a try? And yes, of course, I answer for you to find the fx. It's really substitution by now. Yeah? Substitution. Come on. I'm sure you can do it. I'll give you about 2-3 minutes, same thing. Just wiggle your way through, and hopefully you'll be able to get a nice answer. In this case, the A will be 2r. The A will be 2R. A square. This is A square. Oh yes, of course, you are correct. This should be 4R square. Thank you for bringing this out. 4R square. Then this should be 2R. Thank you. Yep. And this 2R cancels with this 2R. GM rho divided by root 5R, which is equals to GMM upon root 5 R square, and it is 2R, so it should have a 2. Ta-da! If you do everything correctly, it should look something like that. The really life-threatening question would be, if I were to tilt this by an angle of theta, find the force as a function of theta. That will be, because it won't be symmetrical, agree? It won't be symmetrical now. That one really will die hard. So if you can't sleep, remember Madam talked about, some of you can't sleep at night. You want to try that? It will put you to sleep. Sorry? No, I mean sometimes when you do it, for some people this is therapeutic. For some people this is therapeutic, right? I mean it's like, whoa, they get high. It's like, whoa, man, this is music to some people. Right? This is music to some people. So instead of counting sheeps, you count like integrals or like integrals jumping. Can? If you spot any mistake, I might be wrong, so I may have made some careless mistakes along the way. So please, yes, Hannah is looking really cautiously. Sorry? Which one, from here to here? Oh yes, I did. Because what I did was that I substituted R over here and then minus R, this substituted R minus this substituted minus R, but because it's all positive over here and this becomes minus, so minus becomes plus. And that's why I immediately put 2R over here. No, you didn't. So say we call this whole thing K. So this will be Y upon K. It will be R upon K minus R upon K, which is actually 2R upon K. That was what I was doing. Yeah? I skipped a step. You're correct. So the final expression is really beautiful. Don't you agree? It's simplistic. I mean, it's really nice and simple, and ta-da! Then you can, like what I say, if you really want to challenge yourself, think about this. If I have a rod over here, I tilt the rod at angle theta. find the resultant force on that rod. Or probably something different. I mean, like this, you have a rod here, then you tilt it at the angle theta. So how's the force as a function of theta? Okay. Now, it might have application in space travel. I mean, say for example, you got an extended, say for example, you got a really huge object flying, orbiting around the Earth, cutting across the magnetic field to generate electricity. And then the big object orientation may rotate different orientation. It actually does affect the force. Yeah. When you're talking about solar sail, you're talking about probably a sail that is a few hundred meters to 1 kilometers in diameter. And that kind of thing, when you orientate, it does make some change to the gravitational force. So you never know, this kind of things, yeah? Cool. So let's do a quick revision. We started off with something really friendly, which is the two-dimensional one, remember? Two-dimensional forces. And then we went on to the how we built from the idea of circular motion equals to projectile motion kind of thing. And then I show you how Newton actually derived the 1 upon r square idea. And I also show you how the mass of Earth was calculated. Then that's where the friendly stuff ended. Then we went on to the integral stuff. We started off with a rod this way, then we started to tilt it vertical. Yeah? And along the way, I actually show you many techniques. I show you that you can break down a mass into dx, a dm into dx, remember? And I also showed you inherently, subtly, I show you the idea of symmetry. The idea that vertical forces cancels out, that's symmetry, that's an idea. So in a lot of physics questions, Olympic questions, you're going to see this idea about symmetry being applied. I'll show you as it goes on. Can? And then eventually we went through the math of things and then plow through and eventually this one. Some of you may be interested to know whether in physics Olympiad you're required to remember this integral. In the past you're supposed to, but right now usually they're quite friendly. They'll give you the standard integral. Can? But of course, come on, integral of 1 upon x, they don't expect them to give you. Yeah. Why is integral of 1 upon x? Luckily, correct, hold on, next, correct. Ken, so with this, I think we can stop the video and